colloquium of the semester. A reminder that next semester we will have also a colloquium series of the Israel Physical Society, so stay tuned. Also, before we start, I want to remind you, as the IPS representative over here, that we have an IPS conference, virtual conference this year in February, and the deadline for submission abstract and to register is the 22nd of January. So all of you, please do so. We need you and we want you there to speak, to tell about your research and to listen to other research activities. So it is a great pleasure to us today, Professor Anne Lollier from Lund University, Sweden. Really a great pleasure that you can come to deliver a talk in the IPC sessions. And perform a Master of Science in Theoretical Physics and Mathematics. After the theoretical master, she switched to PhD in experimental physics on multiple ionizations in laser fields of high intensities at the Saclay Nuclear Research Center at France. Later, she performed postdoctoral studies at Gothenburg in Sweden, and then Los Angeles, California, in the US. She received a permanent position at the Saclay Nuclear Research Center, and in 1992, she took part in an experiment in Lund, the first experiment of a titanium sapphire solid-state laser for femtosecond pulse laser in Europe that was installed in Lund. And since then, she is one of the pioneering leaders in the field of ultrafast physics, attosecond science. In '94, she moved to Sweden, where she is now a professor. She became a professor at '97, and she led a group of attosecond physics group, study the extreme ultrafast movement of electrons and harmonic generation, again, attosecond science. In 2003, she and a group beat the world record with the smallest laser pulse of 170 attoseconds. She received many awards and she served the community very well and was in the Nobel Committee for Physics between 2007 to 2015. She is a member of the Swedish Academy of Science since 2004. She received the Julius Springer Prize in 2003, the UNESCO L'Oreal Award in 2011, the Carl Zeiss Richards Award, the Blaise Pascal Medal, and the honorary degree of University of Marie Curie in Paris in 2013. And she is also elected as a foreign associate at the National Academy of Science in 2018 and recognized in 2018 with the prize of fundamental aspects of quantum electronics and optics by the EPS. So today she will deliver a talk about attosecond pulses for capturing electron dynamics, and the stage is yours. I will be on the chat and you can write questions, and after the 45 minutes, we will have a session of questions, Q&A. So, Anne, thank you very much.
Thank you very much. Good afternoon, everyone. It's a pleasure to talk to you, even from far away as I am. Thank you also for this very nice introduction. So I'm going to introduce the field of attosecond physics to you. The title of this talk is Attosecond Pulses for Capturing Electron Dynamics. This is the outline. First, I will do a brief historical introduction to this field of research. I have had the privilege to be in this field almost from the beginning, so I'd like to tell you a little bit its history. Then I will discuss the attosecond sources, their versatility, and maybe go into more details about modern and compact sources as we can make them today. Then I will discuss application of this source and especially how we study in time photoionization using attosecond pulse. And I will take as an example photoionization of xenon in the 4D shell as well as autoionization in helium. So this field, I think, started at the end of the 80s when by looking at the light that was emitted by an ensemble of atoms when exposed to a strong laser field, one discovered that emitted a lot of high order harmonics of the laser field were emitted. And you have on the right harmonic spectrum obtained in neon. So what you see is the intensity of harmonic lines as a function of energy. And you see that we are in the extreme ultraviolet range of the electromagnetic spectrum. And you see very nice lines with almost the same intensity. And these lines corresponds to a multiple, odd multiple of the laser frequency. So we have this plateau where all the harmonics have the same intensity, more or less, and this finishes with a sharp cutoff. The increase that you see on the left is simply due to the response of the spectrometer in this case. So you should imagine a plateau starting from 0 and going to this cutoff. So immediately after these first results, the question was raised, do we have attosecond pulse? Indeed, if all of these harmonics are phase locked in time, in phase, then by interference, you confine light into very small intervals. And there is a possibility, as was mentioned by Ted Hench and Steve Harris here, there is a possibility to create pulses in the attosecond regime. So the question was raised, are these harmonic phase locked? And the understanding came a few years later, both through numerical solution of the time-dependent Schrödinger equation by Ken Schäfer and Ken Kuehnen, and also by the elaboration of a very intuitive three-step model by the same authors and as well as Paul Korku. So this works led to the understanding of this high harmonic generation. And you have here a picture showing this, illustrating this three-step model. You have the Schrödinger equation, which describe, at least for hydrogen here, what is happening. So we are in a regime of strong laser atom interaction where the laser field interaction here described within the dipole approximation is comparable to the Coulomb field, which is binding the electron to the atom. And in this condition, you can have a tunneling ionization for a given instant of the laser field. Then the electron is driven away from the atom. It's pushed back towards the atom when the field changes of sign. And then there is a certain probability for recombination. And in this recombination, there is emission of a very short light pulse, attosecond pulse, in the XUV range. So now if you think that this process repeats itself twice per laser cycle, once on one side and then the next half cycle on the other side, you have the emission of a series, a train of attosecond pulse with a sign flip between consecutive pulses. And if you consider the interference of these attosecond pulses, you go into the frequency domain and you find that the power spectrum is made of high order harmonics of the laser field with odd order. Separation between consecutive peaks here is twice the laser frequency. So we have now interpreted our high order harmonics as interference between attosecond pulses which are created in this process. So in addition, there is also a few harmonics, low order harmonics, that are created through the maybe more well-known nonlinear optics process, third, fifth order harmonic generation. So we have now interpreted the generation of these high order harmonics as interference of attosecond pulses, which is equivalent to how I started with, which is that attoseconds pulses are coming from the sum of phase-locked high order harmonics. It's two different ways to see this process. High order harmonic generation, or the generation of attosecond pulses, is also a nonlinear optics phenomenon. It is not the response of individual atoms to a radiation field. It's really the response of a whole medium to the field. So in order to have efficient harmonic generation, you need to have all of these small atoms emitting at the same time and emitting in phase. So basically what is needed is that the phase velocity of the fundamental field, which is driving the process, needs to be equal to the phase velocity of the harmonic field that are generated. This is described by Maxwell equation or wave equation. And how can this be done? I'm showing here a plot representing the refractive index of material as a function of frequency. So how can we have the phase velocity of the fundamental equal to the phase velocity of the harmonic field? Normally, this is not possible because in the visible or infrared, which is the wavelength of our laser, the refractive index is larger than 1. And in the extreme ultraviolet region where these harmonics are generated, the refractive index is less than 1. However, at the same time as harmonic generation, there is also ionization of the medium. This is part of the process. So we create free electrons, and these free electrons are going to change the refractive index for the fundamental field. This is the fundamental field, assuming that we have a neutral medium. But now we create free electrons in the medium, so we add a negative contribution to the refractive index, which will make possible for high order harmonic generation to be phase matched. Typically, this requires an ionization degree of the medium, which is a few percent. So there is a certain intensity region at which this process happens. You need a strong intensity in order to have this strong atomic response to the radiation. And you also need to have enough intensity to create the few electrons that are needed for phase matching, but not too high intensity so that you would ruin phase matching. So it's a really well-defined intensity region where this phenomenon happens. Now, it took several years to show in the laboratory that indeed we had attosecond pulses in this process. And this was done almost at the same time in two groups, one in Paris, a group led by Pierre Agostini. They used an interferometric technique called RABBIT, like reconstruction of attosecond beating by interference of two photon transition. I will mention this technique later. And then almost at the same time, a group led by Ferencross then at the Technical University of Vienna showed the production of a single attosecond pulse and identified this pulse and measured this pulse using the so-called streaking technique. And both techniques are actually cross-correlation techniques where a probe field is used to characterize the attosecond pulse, which can be either in a train or single attosecond pulse. And the medium that is used for the cross-correlation is a gas of atoms, and the process that is used is ionization. Electrons are produced, and the characteristics of these electrons are measured, and in order to characterize the attosecond pulse, one assumes that these electrons are a good replica of the attosecond pulses. Now, since this time, the beginning of the millennium, attosecond research has really expanded quite a lot. Now there are many groups in the world doing attosecond physics. I think it's great to be able to give these talks online and to maybe not to travel. It's good for the climate, and it goes fast. But on the other hand, you miss the travel aspect. So actually, I made the effort to look at an Israel map and to try to see where is attosecond physics done in Israel. And here a list of groups. The group of Neri Dudovic at the Weizmann Institute has been working in attosecond physics almost 20 years. I would like to say there is a very strong, actually, attosecond physics community in Israel. And then you have groups at the Technion, at the Ben Gurion University, and also at the Hebrew University. And if you are listening to this talk and you are doing attosecond physics and you are not in this list, please don't take it badly and send me an email afterwards and tell me what I should have known. Okay, let me now describe to you why this, maybe a reason why this field of research is expanding. One of the reasons is that it's actually easy to make attosecond sources, and they can be very different. They are very versatile. And the reason for the versatility of attosecond sources is, first, there is a inherent geometrical scaling to the source. We can scale down or scale up our source and still keep the same conversion efficiency. Here's a comparison of two situations. You have a certain laser with a certain energy. You focus into a gas and you get harmonic pulses out with a certain energy. You can simply scale your input energy, your medium, your focused area by the same factor. You need to scale down the pressure in your interaction region by the same factor, and you will get an output energy which is scaled up by the same factor, which means that the conversion efficiency is the same. And that leads to sources that varies by several orders of magnitude in performances and in size. You have a compact source that you can see here, which is driven by a laser which is included in these boxes. I will describe this source in more detail in a moment. And this is a vacuum chamber where the harmonics are generated. It's about one meter long. And you can have much larger setups, such as the one that you see here, which is driven by the terawatt laser of the Loon high-powered laser facility, which is coming through a wall here. And then we here focus harmonics with a very long focusing geometry in order to increase the interaction region and to produce harmonics with a high energy per pulse of the order of microjoule. And so this setup here is about 12 meters long. And there is also a facility which is being built at the moment, which is actually almost completed. The setups are almost all running. The Eli facility in Szeged, Hungary, and where you have even larger setups. Now, there is not only a geometrical scaling, but also a wavelength scaling. The process can be scaled with the laser wavelengths, and actually the maximum photon energy that you can produce scale as the square of the laser driver wavelengths. So if you use a mid-infrared laser source, as you can see on this plot, you can produce photons in the X-ray range and even in the water window. As you can see here, these are results from the group of Henry Captain Margaret Murnane at University of Colorado. So possibility to extend these attosecond pulses in the X-ray domain. Normally, we use linear polarized laser light, and we produce linear polarized harmonics and attosecond pulse, but there are also schemes to several methods actually, and many of the works have been done actually in Israel by Israel groups here. You can create harmonics and attosecond pulse with circular or elliptical polarization. You can control the polarization state, and you can even produce harmonics or attosecond pulse with orbital angular momentum. And there is a lot of research in this area. Let me now give you more details about one of this source, and I think a source which has a lot of potential is compact source, which is driven not by a standard laser, but by an optical parametric amplification scheme. It's optical parametric chirp-pulse amplification system, producing only 10 microjoule laser pulse, short pulse, 6 femtosecond duration, 200 kilohertz laser repetition rate, and with stability of the carrier envelope phase of our laser, which is needed in very often in experiments. So the architecture of such a laser is rather simple. You start with an oscillator. This oscillator is seeding amplifiers, fiber amplifiers at 200 kilohertz. The main part of the oscillator is going through a shaper and is then seeding optical parametric amplifier. And we have this characteristic here, about 6 femtosecond at 200 kilohertz repetition rate. So this is a typical attosecond setup, which we have behind this laser. In this condition, not very high energy per pulse, we need to tightly focus in order to reach this high intensity, which is needed for producing these high harmonics. And so it's typically about 100, actually less than 100 micrometer gas jet, high pressure. We have about 4 bar, and we have actually a catcher in order to catch the gas and keep a good vacuum into our interaction chamber. We can look at the light which is produced using a grating that you have here. And attosecond setup always include an interferometer, which you have here. So there is a probe beam that is recombined with the pump beam here. And then we focus these two beams, the pump, our high harmonics, our attosecond pulse, and the laser into another chamber. How do we decide what is the optimal gas length and pressure? Well, you can of course do some estimate, but we can also do simulation. I would like to say that after this many years of research in this field, we have a very good, I think, description of the process. We can calculate the single atom response by solving the time-dependent Schrödinger equation, and then we can propagate into the nonlinear medium by solving a wave equation. And this plot shows you results of such simulation, which shows the intensity of the 23rd harmonic generated in argon gas in color as a function of pressure and medium length. And we see that in this case, we have an optimal medium length, which is around 40 micrometer, and pressure, which is around 5 bar. And I'm showing now a typical spectrum obtained in this condition. So this is harmonic generation in argon. And what is shown here is the harmonics, which are produced as a function of glass insertion. In this system, we always need to control the dispersion extremely carefully, and we do that using a pair of wedges. And this allows us also to change this carrier phase envelope, which means the phase of the electric field relative to its envelope. And you see what you see here in colors are a few harmonics from the 17th to the 41st harmonic. And you also see a lot of fringes because these harmonics are especially broad and overlap a little bit with each other. And these fringes also shows the stability of the dependence of the generation process on this carrier envelope phase. So from this data, we can actually do a very good guess of what is the pulse train producing these harmonics. And in this case, we have about 4 or 5 pulses, which lead to this spectrum. You can see that each pulses are quite sharp. This is a characteristic of the attosecond pulses produced in this process. They have a strong positive chirp that you see in this spectrum. So now I've come to the second part of this talk, which is about application. And of course, what we would like to do is to look at very fast dynamics. What can move so fast in matter, while electrons move quite fast. So this has been the goal of this research, is to really try to look at, to measure electron dynamics in matter in general. And there has been studies in all kind of system, simple system like helium atoms, neon atoms, larger atoms, to small molecules, large molecules, including biomolecules and even solid state materials. So there is a lot of research in many directions. I'm going to present to you results in, I would like to say, a complex atom. So you can of course use helium, neon, and this is very good to know what one is doing, because the contribution of the atom is not very important. But then it's to do new physics. You want to look at more complex processes, and this is one of these which I would like to show you in this study. And finally, I will discuss autoionization in helium. So how do we measure photoionization dynamics? And especially I'm going to discuss what we call photoionization time delays, representing the time for the electrons to be ionized. So we use an experimental setup very similar to what I have shown. We need an optical interferometer, POM probe setup. We need, of course, a high harmonic generation part. And then we need a photoelectron spectrometer. And the results that I'm going to show you have been obtained with more standard laser system, titanium sapphire, a few millijoule, 1 kilohertz repetition rate. This is the optical interferometer. And then we look at electrons. We measure the electron energy using magnetic bottle photoelectron spectrometer. It's an angular integrated measurement, and but it's a spectrometer with a good spectral resolution, allowing us to do coincidence measurements. So what is the idea behind our measurement? It's a quantum interferometry type of measurement. So let me describe to you the essence of this technique, the rabbit technique. The idea, again, is to measure the electrons which are emitted in a process where the atoms are exposed to XUV radiation in the form of high order harmonics, so leading to these main peaks in blue, and a probe field, which is much weaker than the field which is used for the generation of the harmonics. So you can have absorption of photons from the probe field, leading to the creation of these sidebands in red. So if you consider one of these sidebands, you can see that this is a quantum interferometer where you can reach the state corresponding to this sideband by two ways: by absorption of one harmonics and an infrared photon, or by absorption of the next harmonic and emission of an infrared photon. So two ways to reach the same final state. You have interferences, and it's thanks to this interferometric technique that we have access to phases and time delays. So our interference signal can be written as is shown here. Here tau is the delay between the XUV radiation and the infrared radiation. And on this image, you have a photoelectron spectrum in color as a function of the delay between the infrared and XUV field. And you see that in particular the sideband peaks, which are indicated here by the yellow arrow, oscillate as a function of the delay. And all the physics information is included actually in this phase offset that the sidebands have. And this phase offset is due to two contributions. One contribution is due to the XUV radiation. The different harmonics here can have different phases, and this influence this oscillation of the sidebands. And then there is a contribution from the ionization process, which is maybe the interesting information. Actually, the Rabi technique was developed in the first place to characterize the XUV radiation, and nowadays it is used mainly to determine this ionization time delays, this time for ionization. Now, what is the interpretation of this time delay? There is actually two contributions. One of the contribution is really this group delay of the electron wave packet, which is related to propagation of the electron as it is ionized in the potential of the atom. It's very analog to the group delay of a light pulse going through a material. There is also an additional delay which is induced by the probe field, and which is induced by this interaction that you need to get this interference, this continuum transition, it's called tau CC, which are needed for the measurement to take place. So due to the probe field, the electron wave packet also picks up a phase, which leads to this small delay. Fortunately, this tau CC does not depend very much on the atomic system, and can be calculated to a good approximation. So the interesting information here is in this group delay due to ionization, which is also called Wigner delay because it was introduced 1955 by Eugen Wigner. So let me now come to photoionization of xenon in the 4D shell. So we again, what we look at is ionization of xenon in the 4D shell, and what is happening. Here is a picture of the cross-section, ionization cross-section as a function of energy, and you see 4D ionization presents a strong resonance it's called actually giant dipole resonance, which is peaked at 100 eV, which is very, very broad in frequency, and which has been interpreted in the past as a collective response of the 4D shell to the XUV excitation. So the question is, can we learn something using trying to get some temporal information on this process? In addition to this giant dipole resonance, you also have interesting phenomena happening close to the threshold. You have an effect of the spin-orbit interaction and an anomalous branching ratio between the different spin-orbit channels, leaving the ion into different states, 4D 3/2 or 4D 5/2. And finally, there is also Auger decay. When you ionize xenon into the 4D shell, the hole can be filled by an electron 5s or 5p, and then another electron can be emitted. This is Auger decay. So can we see somehow the dynamics of these different processes? So we do experiment, and I'm showing here coincidence map with XUV only and with XUV and infrared. So what you see here is the probability to get certain electron pairs with as a function of energy. So what you see is different islands corresponding to absorption of different harmonics, and with a decay into a certain Auger line. So the different horizontal line here corresponds to Auger lines, whereas the vertical lines corresponds to absorption of some harmonics. So you see here absorption of, for example, here the 57th harmonic with decay in this Auger line. When we add the infrared radiation, we see additional islands, which corresponds to the this creation of these sideband peaks. So the experiment consists in taking these coincident maps and then changing the delay between the infrared and the XUV, and then looking at the oscillations of these sidebands, and then comparing the phase offset of these sidebands. And here's the main results of this experiment. You have here these time delays. The experiments have been calibrated with respect to ionization of neon. So I'm showing you absolute time delays here as a function of photo energy. And you see here for the two finest state of the ion, 4D 3/2 and 4D electron 4D ion in the 3D 3/2 and or 5/2 state. The calculation that you see here have been done by relativistic random phase approximation, agree quite well with the results. And what you can see here is that at high energy, these time delays are very close to each other, and they are actually positive. And whereas at threshold, you have a strong difference by more than 100 eV between the two results. So how can we understand first what is happening at threshold, and also the origin of this positive time delay? So let's use the simulations and look at the different channels for the photoionization. And I'm showing here a calculation showing the main channels which are important for the photoionization. This is 4D to F channels. And you see that two of these channels contribute mostly to this giant dipole resonance that you see here. And at threshold, the three channels, including this relativistic spin flip channel, which is the red channel, contribute almost equally, and actually around threshold, you see evidence here for interference. You see that these different channels oscillates as a function of photo energy, and obviously there is quantum interference happening at threshold. So now let's use our techniques that we have developed in ultrafast optics to disentangle these channels and to look at the time evolution of this process. So what we now do is we take one of these channels and we do a time frequency representation. What is shown here is a Wigner distribution, which is an autocorrelation of the amplitude of one of these channels. So as a function of time and energy, and you can see on this graph two different mechanisms that happens. One, which is happening very broad in frequency, in energy, and fast in time. So you have a broad resonance here, very fast in time, and this corresponds to the giant dipole resonance in the 4D shell. So there is a maximum at 100 eV. The duration is a few tenths of attosecond. It's a very broad band. And then you have a narrow resonance at threshold, which is related to this spin orbit interaction. This resonance is much narrower. It's about a few electron volt bandwidths, and it's peaked at 75 eV, and it has a duration of a few hundred attosecond. So you see that thanks to these measurements and the analysis which has been done, we are able to disentangle the different ionization mechanism. One which happen mostly at threshold, which is coupled to a spin orbit interaction and spin flip. Takes a few hundred attosecond, rather narrow in energy. And the second process is this giant dipole resonance of the 4D shell, which is very broad in energy, very narrow in time, a few tenths of attosecond pulse, which corresponds to the measurement of a photoionization time delay. So I would like to conclude this talk by showing you some results now longer in time. We are looking at the autoionization of the S2P doubly excited state in helium. And this is the prototypical example of a phonoresonance quantum interference process where you can ionize an atom, helium, either directly or via a discrete bound stage, which then decay by autoionization. This process, which is very well known, has been actually described theoretically in a beautiful article by Hugo Fano in '61. And in Fano's derivation, he described this process with the help of an asymmetry parameter, which depends on the ratio between the amplitude for direct ionization and the amplitude for ionization via the discrete state. So depending on the value of this asymmetry parameter, you have this beautiful interference curves, which are indicated here. And for helium, the asymmetry parameter is actually equal to minus 2.67. So this is the blue curve that you have here. Corresponding to this cross-section, you have, of course, a phase variation, the phase of the transition amplitude, what you see here, which indicates a pi phase jump at threshold. So this was the motivation of our experiment, is to look at this process, which is well known, has been studied in the past a lot using, for example, synchrotron radiation. So our motivation was to look at this process and see, oh, can we measure the phase, and can we learn something more by measuring this phase. And the method is the same as described previously, using this sideband techniques using this rabbit technique and reading the phase, which is induced by this phonoresonance into the sideband amplitude, into the variation of the sideband with delay, exactly as I explained before. And this is the result that we obtained. So we are looking here at the 38th sideband. We excite the phonoresonance using the 39th harmonic, and we look at the phase by looking at the amplitude and oscillation of the sideband. And this is the result. You have the amplitude, which really goes through a deep minimum. This is due to the Fano process, to the interference, where both way to ionize have the same amplitude and opposite phase, and then the very nice phase variation, almost a factor pi, as predicted by the theory. I would like to say that to be able to have this type of precision measurement and this type of very nice, for example, phase jump, we really pay attention to we try to perform a high spectral resolution measurement with high spectral resolution of our spectrometer, of course, but also we use the narrowband probe field in order to really probe the resonance the best possible way. So when we have done that, we can also do the same type of time frequency analysis to look at the when do this process happen in time. And you can see on this Wigner distribution, which is shown here again, these two processes, the direct photoionization, which you see at short time. This happens very fast, and it's a broadband. And then the autoionization process, which takes a longer time, typically a few tenths of femtosecond, and which is narrower in frequency. And you see also a strong interference, and this very strong interference here in the middle, which corresponds to this minimum in the cross-section. Now, phonoresonance, where are we going by studying this process? Phonoresonance are also interesting to look at the coherence of the electron wave packet that we create. And this can be done by letting the symmetry parameter be a complex quantity. And we try to study the coherence of the electron wave packet, which is created. In this case, we have a system which is actually closed, and we don't really need to let the asymmetry parameter to be complex to describe well the process. The red line is what you can get by letting Q to be a little bit complex, and the blue line is by assuming it to be real. So we believe that in this case we have an electron wave packet which is very coherent, but we are looking at other systems where we can see actually decoherence of the electron wave packet. So this is a little bit the direction that we are doing in this case, is with can we do a quantum state, I don't dare to say tomography, but try to characterize the quantum state of electron wave packets. So with this, I would like to conclude. I tried to give you a little bit historical introduction to this subject. Then I presented to you the status of what we can do regarding attosecond sources. And in the second part, I try to illustrate and explain how we can look at electron dynamics in matter with example xenon and helium. With that, I would like to thank you very much and thank my colleagues for this work. You have two groups here. one working on this 200 kilohertz laser system and this modern and compact attosecond sources, and the second one here working on this electron dynamics studies. And of course, I would like to thank my two more senior colleagues, Cord Arnold and Mathieu Gisselbrecht, and also theorists, which are very important to in this physics. So thank you for your attention.
Thank you very much, Anne. The stage is clapping here. Everybody's clap. Okay, thank you. The stage is open for questions. So someone wants to ask, just press unmute because I muted all of you. Okay, so maybe I will start. You showed several examples on molecules. How about like condensed matter systems? Where this field is going to this direction?
This field is definitely going into this direction a lot. And it's going into condensed matter different ways. First, groups are using solid state material to generate harmonics. You get a lot of information on the system by simply generating harmonics. And this is a huge field of research, which I have not mentioned, which I have not contributed myself. And it's been driven by Paul Korkum and co-workers. Neri Dudovic really has worked a lot on this field. So you can study a lot on your molecule, on your solid state system by simply generating harmonics, and so this is one field of research which is really developing very much. And you can also put your solid state material in the application chamber and looking at photo emission, and you can look at the photo emission time delays. You can look at, and what we actually are trying to do in our lab is to try to, this has not really been done yet, but it's I think it's coming very soon, to be able to combine spatial and temporal resolution to look at specific things on your sample nanostructure and look at get some temporal information on this nanostructure, for example. So it's just I think it's going to explode into solid state physics, this field. And in addition, you can do that in rather small labs. So it goes very well with solid state physics, I think.
Thank you very much.
May I ask a question, please?
Yeah, of course, Abraham, go ahead. And after that, Ribeiro from Brazil wants to ask after you.
Do you want me to stop sharing, maybe, or to?
No, please keep the transparency.
Okay.
The way it was. First,
right.
thanks for a very interesting talk. I'm really interested to find out. Can you elaborate on the measurement of this electron wave packet coherence? What do you measure?
We actually measure. We measure the phase and the amplitude. Okay, this is what we measure. But we're actually going into yes. So we measure phase and amplitude. When we do that, we more or less assume that we have a coherent, we have a pure state. But what we would like to do, and this is one direction I would like to take, is to skip this assumption of a pure state that we kind of automatically make in this type of measurement, and try to characterize the quantum state of this wave packet. And we actually, this is something I didn't show because it's really preliminary. So let me show that. We have an indication. This is really preliminary, But this is a measurement where we don't look at sideband 38 as I showed, but we look at sideband 40. Okay, so the same measurement, we just look at different sidebands, and we don't get the same result. Although if this was completely closed system, we should actually obtain the same result with a sign, should be minus sign instead of plus sign, but we don't. And you see that we don't have the same very strong interference in the amplitude, and the phase jump is actually much less than pi in this case. And a possible interpretation is that what we have here might be, okay, might be this is not a closed system in this case, and we have actually another bound state here, 2p² state, which actually where you can have transition. So again, this is completely preliminary. We need to make sure that we understand what we try to understand what is the difference between sideband 40 and sideband 38, and is it due to the fact that actually this electron wave packet is not as coherent. So this is my way to elaborate, but this is really progress it's in progress.
The electron
Okay, we have
is coherent in the sense that it has an area of h bar, but it has a shape too. Is this what you mean?
I mean, I don't know. I mean, this. I don't know how to answer this question. When I say it's coherent, that means it's completely deterministic. You know everything. But the question is, can we really do that? I don't know.
Thank you.
Okay, we have another question, Ribeiro from Brazil, I think.
Right, yes. Anyway, thank you for this nice talk. I would like to understand more the electron correlations. In that graph before phonon resonance, when do you consider the spin orbital effect? Yes, in this one.
Yeah.
How do you characterize the electron correlation effects?
This one, the 4D. This is your question, or?
Yes, yes. My question is, you explained the reason why you have a broad region in the time, and you think that this is because the electron correlations. I would like to understand if you know how to characterize more these electron correlations.
I think this is actually well known. It's from the 1780s. I go back to maybe the introduction slide. This big resonance here. It is due to correlation effects in the 4D shell, polarization effects. If you want, you have a screening effect due to the electron in the 4D shell, so that you have first. The ionization is first reduced, and then you have a resonance which happens at 100 eV. It's very huge. So what we measured is first of all, of course, we also see this, but in our measurement, now I'm going to the measurement. We measure this resonance that we see in time. We see this. Decay, the time delay are positive, and they are very seldom positive actually in all these measurements, but this time they are positive and they are small, and we think that this corresponds to this resonance. Positive delay, which is slightly increased as you see here, and which corresponds to this correlation effect.
Right.
Okay.
Thank you. I could understand.
Okay, so I think, sorry?
I can make another comment, which is more general. We are not, maybe we are doing atomic physics here, and we are looking at processes which people have looked at many years ago, actually using synchrotron radiation. We do that with our technique, as attosecond technique. And the difference is that now we are able not only to measure the cross-section, but even the phase of this, the delay or the phase variation across the resonance, and which gives us another angle to look at this ionization mechanism and look at them. So maybe it's not completely new in that sense. This is the same ionization mechanism we look at that people have been looking at in the past, but now we have more information, which is this phase information, and this allows us to when you have phase and amplitude, you can do Fourier transform, you can do time frequency analysis. We are allowed to look at this in the time domain. So yes, this was my comment.
Thank you, Anne. Thank you for your answer.
So thank you very much, Anne, for the wonderful talk and for coming and speaking with us. I hope that you had good listeners also. For all of you, so we meet again in the IPC's next semester. We will send the list of speakers soon. Also, I remind you again that you need to register to the IPS annual meeting, a virtual meeting that will be held in the 22nd of February, and the deadline is the 22nd of January. So have a nice evening, and thank you, Anne, again.
Thank you very much. It was a pleasure.
Thank you, Anne.